Hello, lovely people. Today we will be looking at a slew rate. We're going to try to figure out what that is. We're going to try to visualize it, and we will measure these two amplifiers as well. So since I started measuring amplifiers, a lot of people are bugging me about the slew rate because we're measuring distortion, yeah, and a lot of people say that distortion doesn't mean literally anything, and the most important thing that describes how an amplifier is like SQ, how quality sound it reproduces, is the slew rate. So what is the slew rate? Now I have my generator, I have my oscilloscope, and before we measure amplifiers, we need to have some kind of a benchmark and to know like what we're aiming for, and just to make sure that our equipment is better than the actual amplifier. Exactly the same with measuring distortion. We need to make sure that the audio interface has lower distortion than the amplifiers we're going to be testing. So just for the future, we're going to be testing two amplifiers, which is, one of them is Alpine BBX, which is a two-channel, super cheap budget, very poorly performing. And on the other side of the spectrum is my lovely 409 with the copper backplate. So this is basically one of the worst amplifiers that I have, and this is one of the best amplifiers that I have. Both of them are class AB. We'll be measuring class D later on because the class D is a bit tricky and different. I'm gonna tell you why and explain you. So let's talk about the slew rate and what it actually is. So I do have this generator that can generate various waves. So I have sine wave, square, triangle, and yeah. So on a regular sine wave, you have like peaks and dips, and it's just a regular sine wave. If you try to look at a square wave, what a square wave is, it has extremely sharp edges. Yeah, so basically a square wave kind of in an amplifier would represent an infinite impulse. So it's like the first edge, it should be like infinitely steep. And basically what it does, if you feed this signal into the amplifier, it's not going to reproduce it 100% exactly the same because of the capacitance and everything in the amplifier, so it cannot. And depending on how good it reproduces the square wave, some people say that's where the quality of the amplifier comes. That means that it can potentially respond faster to transients, to like very high energy in music. So imagine if you have like a sine wave, but it's very high in amplitude, this edge becomes not that soft, but it becomes something like this. You can see very steep, and obviously the higher the frequency, the steeper the edge, but at the same with energy. So if we go look at the square wave again, what slew rate is basically the difference between how long it's gonna take for the wave to rise. So if so now I'm measuring the actual generator because I want to make sure that the generator is better than the amplifiers. So we're going to measure the slew rate of the generator, and then we're going to have like a ballpark. Is it good enough? And then we're going to measure the amplifiers as well. So to measure the slew rate, we're going to zoom in quite a lot. So now you cannot see like these edges, but it's just only this, it's focusing on this. And we're going to zoom in more, and you can see what starts to happen. It starts to kind of soften the edge, and it's just limitation of the actual, probably, I don't know if it's the scope or the generator, but a combination of both. And the amplifiers are gonna have exactly the same thing, but it's gonna start much earlier. So the slew rate is, I'm trying to fit as much as I can into one, there we go. So if I'm gonna zoom in very a lot, the slew rate is the difference between the time it takes for the wave to rise. So a scope has some measuring tools, which is these cursors. If I choose the cursor and I'm gonna do track, see, I can put these cursors wherever I want. So I'm gonna put first one at the bottom, and then the second one I'm gonna put somewhere on the top. And then this, we have these measurements. So the difference in time is 104 nanoseconds, and the difference in voltage is 9.6, 9.5 volts. So we need to do some basic math. What we do is we take 1 millisecond divided by 0.104, 0.104 equals, and then times the voltage, which is 9 point, let's say 9.5, 9.5 volts. And we have a slew rate of 91 volts per microsecond. So the industry standard is volts per microsecond. And we will see how good these amplifiers are. Now this, what does the slew rate depend on? The slew rate does not depend on frequency. Let me show you. So with this generator, now I'm set at 20 kilohertz. And with this dial, I can change the frequency. So watch like this one and watch these numbers. So if I reduce the frequency, you see 18, 13, 10, here 7. The frequency reduces, but these numbers don't change at all. If I'm gonna go even higher, click, I'm gonna go to 200 kilohertz, the numbers are the same. So the slew rate does not depend on frequency. See, I'm changing it from 20 all the way up to 100. It doesn't change on the frequency. So we could potentially measure amplifiers at 1 kilohertz, at 100 hertz. It doesn't matter. What matters is the voltage. So this is the level of peak to peak. So let me just try to show you. If I'm gonna see, I can reduce the voltage and I can increase the voltage. And watch what happens with these numbers. So the time is gonna be the same because the cursors don't move. The cursors move up and down. So the voltage is different. So you see, now we have 7. If I'm gonna reduce it even more, 6, 5, 4, 3. But if I'm gonna increase it, 7, 8, 9, 10, basically it increases. So the slew rate depends on voltage and not on frequency. That means that we could test amplifiers, as I mentioned, at 20 kilohertz, at 10 kilohertz. It doesn't really matter. What matters is to set a standard for the voltage that we're trying to measure the amplifier. And this is the thing, because this amplifier is kind of weak, so it's not going to have a lot of power. It has 20 watts, 25 watts something, but that one has 60, 70 watts. So it's not fair to compare the slew rate of these amplifiers at maximum power, because obviously that one is going to have a higher voltage, where it's going to be the higher slew rate. So to set the standard for measure amplifiers, there's no standard. That's the thing. So I have to I'm gonna do this for myself because I don't know if anybody else is gonna do it. So my standard will be, I'm gonna go to measure. My standard will be, let me just reduce this. Auto set. Auto saves you from everything. There we go. So measure, there we go. So I'm thinking to have a standard of square wave of 10 volts RMS, which is 20 volts peak to peak, something like that. 21, 22 volts. If I would switch this to sine wave, that represents 7 volts RMS, which if we do basic math into Ohm's law, that would give me into 4 ohm load, that's going to be about 10 watts. So 10 watts of power at 10, 20 kilohertz, it's a bit too much. but on lower frequencies it's fine. So I think we're gonna keep it, I'm gonna keep it at square wave 10 volts RMS. So this is going to be like the standard to compare different amplifiers. And then what I'm going to do, I'm going to try to measure the amplifiers at maximum voltage just before clipping, just to see how much that amplifier is capable of. Because again, as I mentioned, the slew rate depends on the voltage, not on the frequency. So it's going to be two measurements. One is going to be just for comparison at 10 volts RMS, and the second one at max power, just to see what the amplifier is capable of. So I'm going to show you a few measurements now with these amplifiers, but in the future, what I'm planning to do, I'm going to measure all the amplifiers that I have, and this scope has a print screen button, which you can save to USB. And then I can have like this actual screenshot. Instead of taking the picture with my phone, I can have the screenshot with the cursors and everything. And that I'm gonna post into Facebook, into my group Distortion Factory. And we're gonna compare the amplifiers. So this, as I mentioned, it depends on the voltage. So let's have a look at what is the slew rate of this generator if we crank up the voltage to max. Again, frequency doesn't matter, but let's keep it at 20 kilohertz because why not? And let's do the same. Zoom in, something like that. A little bit more. There we go. So let's put the cursors first. Track, yeah, something like that, and yeah, something like this. So now we have 104 and 14 volts. So if I'm gonna do that basic math again, 1 divided by 0.104, yeah, 104, and times 14, equal times 14, and I have 135 volts per microsecond. 135 volts per microsecond. So if I'm gonna measure an amplifier and it's gonna measure, obviously it's not gonna, but if the amplifier is gonna measure something close to 100 volts, 130 volts per microsecond, then I know that this is kind of a limitation of this thing and not the amplifier, but we're gonna see much lower numbers, I guarantee. So this was on the loopback, basically the scope measuring the generator. Now I'm gonna connect this amplifier and we're gonna try to measure this amplifier first. Now I have this amplifier connected. It's on, so it's kind of the same as measuring distortion. You have a load because it has to be on the load. I have some leads that go through the probe into the scope, and I have this RCA going in, which I control everything. Lithium battery, 13 volts, no issues there. So now, what can we see? We see a sine wave. And basically the same like with any kind of head unit. If I'm going to increase the level, the sine wave goes up, and I'm going to increase it until it clips. So we can see it's clipping with 20 volts out of the amplifier. So I know that like if we go reduce the clip, something like that, 17. So like 17, 16 volts out RMS on the sine wave, it's still clean and it's not clipping. So now I know that I can measure up to this. If I switch it to a square wave, that's giving me 22 volts RMS on the square wave, because square wave RMS counts differently than sine wave. So I'm going to reduce it just a tiny bit, just down to 20 again, something like this. Yeah, that's perfectly fine. I'm going to reduce this frequency a little bit down to 20. There we go. So this is a square wave of this amplifier on maximum power. Because you remember, I said we're going to measure at 10 volts, but this is at 20 volts. So this is at maximum power. So let's measure the slew rate. Again, we need to zoom in. The frequency doesn't matter, but we're going to keep it at 20. Let's zoom in. And we can see here that we have something happening here. And again, as I mentioned, a little bit soft edges. Can we zoom in a bit more? There we go. Perfect. So now I'm gonna have the cursors again. Track. There we go. Now I'm gonna go a bit lower. So how low and how high? The standard for measuring slew rate is 10% and 90%. But instead of actually calculating everything, I'm just gonna eyeball it, because again, this is, for me, it's not supposed to be perfect or anything, so it's perfectly fine. I'm just gonna eyeball it. So I'm gonna put something, one cursor like here, and the other one something like this. And I think it's close to like 90, 10 and 90. And let's see what we have. So we have these numbers. Let's plug it into the calculator. This is the thing. This scope doesn't calculate the slew rate by itself. We need to use some math. So 1 divided by 0.73. 0.73. And times the voltage, 32 volts. 32 volts. And we have a slew rate of 44, close to 44 volts per microsecond. Now, is this good or is this bad? There is a lot of discussion online, and some people say that if amplifier has a slew rate of more than 6, it's good. More than 10, it's even better. So this one having 44 is very good. So this one, as I mentioned, 44. Let's see what happens if I'm going to reduce the voltage, because now we will need to compare this amplifier and this, and we're going to compare it on 10 volts, because this was not 10 volts. So on measure, we have 18, 19. Let's reduce the voltage down to 10 volts RMS. Lower, 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 something like that. There we go. 10 volts RMS. I'm gonna zoom in a little bit, something like that. And now we can see that these edges are a bit different. They look a bit different. And let's go back to the cursor menu. And let's adjust a little bit these cursors. So I'm gonna bring this a little bit higher. Maybe it's not fair, but the thing is, what I want to see is these edges are not as important. What important is the middle part where it rises the fastest. So we have this, something like this. Yeah, let's keep it like this. So before we had 44 volts. Let's see what we have now. 1 divided by 0.48. 48 and times 15.5. Let's say 15.5. 15.5. And we have a slew rate of 32. So you see it dropped by what, 10 volts? And this is the thing. The slew rate, again, it depends on the level, on the voltage, and not on the frequency. And I can demonstrate exactly the same with this amplifier. So, level, voltage, and look at this number, 15. If I'm going to reduce the voltage, the number goes down. So on lower voltage, the slew rate is lower. If I'm going to increase it on higher voltage, the slew rate goes up. The time doesn't change. It stays 480 nanoseconds. See, it doesn't change at all. The only thing we see when we increase the voltage, something here appears, but it's fine. And now what I'm going to do, I'm going to increase the frequency. So now we're set at what, 20 kilohertz? Let's jump to 200 kilohertz. So 220 kilohertz, and we have the slew rate exactly the same. So we can see that the wave is deformed. It's not the same as a square wave, but the slew rate stays the same. If I'm going to reduce it, you see the wave expands, but this edge, it stays exactly the same, and it doesn't change depending on frequency. See? So now the interesting thing is, let's have a look at the actual square wave, because what people do, let me just remove these cursors, cursor What people do, they just look at the square wave because it's fun to look at. So we can see something happening here, which is not perfect, but yeah. So this is 20 kilohertz. Let's increase the frequency. Let me go down and up. Okay, so 20, 15, 30, 40. Actually, let's put measure because this one reacts faster. There we go. So 50. And we can see that the square wave is still square wave. It doesn't represent, it doesn't look like a sine or a triangle. We have something happening here, but this is 130 kilohertz, which is ridiculous. If we increase it more and zoom in a bit more, you can see that the wave starts to deform. And like here, let's increase the frequency even more. Yeah, see, this is basically a sine wave or a triangle wave, but this is 400 kilohertz. So even at like if we keep it at like 200 kilohertz, it doesn't really look like a square wave, but the top is there. But again, this is 200 kilohertz, which is ridiculous. So you can see how the actual visual wave depend on the frequency, because what happens is if you zoom in enough, there we go. Basically, if you have the edge staying the same and not changing, the only thing changes is like this distance. So visually, when you have this distance smaller, smaller, and smaller, it starts to look like a sine wave instead of a square, because if you reduce the frequency, you see, it looks more like a square wave. If you increase the frequency, it looks less like a square wave. But yeah, so this amplifier, we can see it performs perfect up to 20 kilohertz, no problems whatsoever, even at higher frequencies. So 30, 40, 50 kilohertz is still a square wave. Yeah, so you have something here, but 50 kilohertz is still a square wave. Yeah, so this amp was tested by the Russian guy. Again, this is the F409. So it was tested by the Russian guy, and he had exactly the same results as I did. And for me, what's interesting to see is, will this kind of correlate with what we can hear and with the distortion that we're measuring with the audio interface? Okay, so now we know that we have at 10 volts RMS, we have 32 volts per microsecond slew rate of this amplifier. Let's switch everything and let's measure this, the bad one. Now I have connected the smaller amplifier exactly the same way, RCA, 4 ohm load. I'm playing a sine wave for now, and I'm having this. So now I need to find where it clips. So I tried to turn the knob all the way up, and it didn't clip because this amplifier needs a lot of voltage in the input. So it takes like up to 8 volts of input, whereas that one you can max it out with I think 2 or 3 volts, which has a switch with direct mode. So for this I had to turn the gains up on this amplifier to max it out. And here we have, I'm gonna increase the level, no clipping, no clipping, and here we have clipping. So it clips at what, 15. If I'm gonna reduce it a bit, we have 14 volts RMS out. Now, probably you noticed, if I'm gonna start clipping, the top is clipping a little bit more than the bottom, which is not equal, but it is what it is. So I'm gonna reduce it just before clipping, something like this. We have, what, 13 volts? Something, yeah, let's say 13 volts, and we have something like this. Okay, so now we know that this is our like maximum output. Let's see the slew rate. I'm gonna switch to square waves, and we have a square wave. For this one, you can start to see straight away at 20 kilohertz, we already have that round off. On that amplifier at 20 kilohertz, it was totally flat, but on this one we have that round off, and probably you can already see that this is not as steep as it was with that amplifier, but let's try to measure. So we have 18 volts RMS. This is the maximum slew rate that this amplifier can do before clipping. Let's zoom in, something like this, a bit less so I can see. There we go. Let's enable the cursors. Track. Let's put one of them, something like that, on the top, and the other one we're gonna put at the bottom. There we go. Yeah, and let's measure according to this. So what we have 1 divided by, oh, that's 4 microseconds. Okay, so we don't need to divide. So we need to take the voltage 31.6 volts and divide it by, because it's in microseconds, so divided by 4.15. 4.15, and we have a slew rate of 7.6 volts per microsecond. And that one was like, what, 30 something? So that's like 4 or 5 times the difference between these. And you see that this is kind of on the limit that we said that is acceptable, like between 6 and 10 volts. And this, remember, is on maximum output. So now what we're going to do, we're going to reduce it to 10 volts RMS, because we're going to compare this at 10 volts. So let's reduce it, and you know that when you reduce it, the slew rate goes down. Let's reduce it to 10 volts. There we go. Let's increase this. No, too much. Yeah, we can keep it like this. And I think we can keep the cursors in the same places, because this starts to round off, but yeah, it's kind of flat, so we're gonna keep it the same places. If we jump to the cursors, we have 16 volts and 4. So time didn't change, we changed the voltage. So now we have 16. So we had 7.6, and now 16 divided by 4.15, and we have 3.8 volts of slew rate into 10 volts out, which is very, very low. And this was exactly why I wanted to show you this, because again, this amplifier is super cheap. Brand new is like under £100. This is top of the line of the Alpine V12s, and you can see this massive difference. So 10 times the difference almost. Yeah, because that one was 30 volts on 10, and maximum was close to 50. So close to 10 times the difference in slew rate between these two amplifiers. And it's going to be very interesting to see what Class D does, because with Class D we have some problems. Actually, I can show you what problems I have with Class D. So this is a Class D MRX F65. I connected it exactly the same way. I do have one wire for the ground that goes to the ground, because of different grounding planes, it needs to be grounded. It was exactly the same with this. It gave me a protection error because it was not grounded. So yeah, so this is there we go. This is a signal with the generator off. If I'm going to zoom in, we can see a sine wave of 340 kilohertz. So this is what scope picks up as the switching frequency of this amplifier. And this is the thing. Then if I connect my generator, so this is a sine wave playing, and you can see that there is a 17 kilohertz light. Let's do 20 kilohertz sine wave, but on top of it, it's that 300 kilohertz wave that is modulating. And for this reason, if I'm going to switch it, so this, we're going to keep it at 10 RMS. If I'm going to switch it to square wave, you can see this. And this, like, if you look at it, yeah, it looks horrible. But this is just because you have that 300 kilohertz square sine wave riding on top of this wave, and it's not correct, so you cannot really measure it. The way to do it is to have a low pass filter and chop off everything above like 20 kilohertz. So some scopes have that function. This one has, but it has a low pass only at 800 kilohertz, so it doesn't affect that because it's way before that. The other way how to do it is to have a low pass filter, RC. It's just a simple RC filter on a breadboard, so a resistor and a capacitor. Let me show you what it does. So now the only thing that I did, I took the output and connected through this RC filter, and this is the square wave that we have after the filter. So if what I'm gonna do is I'm just gonna just short it and release, so you would see like before the filter and after the filter. So this is after the filter, this is before, after, before. So you see that RC filter, it kind of removes that, but not fully, and by doing that it kind of rounds off the edges even more. So actually, just for fun, we can try to measure this square wave. So sine wave looks already cleaner. This is a 20 kilohertz sine wave. Let's see where it clips. There we go. This is like digital clipping is a bit it looks a bit different than a B-class clipping. So let's remove this. Something like that. Yeah, we have about, probably we can do like 20 volts, but let's do it 18 volt. Let's switch to square wave. And see, it's kind of flickering, it's kind of doing something, so I don't know. Let's put the cursors. Okay, so we have the cursors kind of in good positions, and we have 8 microseconds, 36 volts. So this is going to be a very, very low slew rate. 37.2 divided by 8.3 microseconds, 8.3, and we have a slew rate of 4.5. So 4.5 volts slew rate on maximum output. If we reduce this to our standard 10 volts RMS, you can see that it's gonna be very, very low. Okay, 10 volts. We're gonna go to cursors again. We can increase this. Oh yeah, this looks fine. And now we have 18 point, let's say 18 volts only. 18 volts divided by 8.3. We have a slew rate of 2 volts per microsecond, which is extremely low. So basically this is a slew rate of a sine wave. So basically this class D, if we look at the square wave, it can barely reproduce the sine wave at 20 kilohertz, and that's why people say that like class D, it's bad for the higher frequencies. But again, I don't know. It depends how much this is audible. A lot of people say that they claim that they can hear the difference, but I am planning to do the actual AB listening test between them and just to see if there is an audible difference, because it's very similar to the distortion, THD. What is audible, what is not audible. Same with the slew rate. What is audible, what is not audible. So if we compare like this class D with that, it's a massive difference in slew rate. And yeah, some challenges, but fun. So this is just a example for you how to measure slew rate, how I'm gonna measure it at maximum power at 10 volts. With the RC filter for this class, for all the class D, because I will be testing my X class. Basically, I have like 25 amplifiers to test the slew rate on and to calculate it. And everything, as I mentioned, is going to be posted into the distortion factory. It's just I need some time for the measurement. So I hope you enjoyed this video. I hope you learned some stuff. If you have any experience with slew rate, please comment below. And thank you very much for watching, guys. I will see you in the next one.